Before we get into the lesson on circles, I want to talk about something else. It seems unrelated at first. So let's do some stuff that you already know how to do. Let's start with factoring a little bit. So let's factor x squared plus 14x plus 49. You're probably thinking, Mr. Reader, really? We're going through this again. We've been through this. This is elementary. I agree. So let's hurry. But I'm going somewhere with this later in the lesson. So we do this. Two numbers multiply together give me 49. Add together give me 14. They must be 7 and 7. And notice they're the exact same thing. X plus 7 and x plus 7. Both quantities are the same, so therefore we can write it like that. Okay, no big deal. We all know that. So here's the catch. Suppose I wanted to give you something that was going to turn out to be something like this, but you didn't know what number was in the middle. I'm sorry, you didn't know what number was at the end. So I basically walked up to you and I said, hey, what number goes in that blank to where when I'm finished with this thing, I can factor it and I'll be able to write it like that. So before you blurt out your answer to yourself or write it on your paper, let me give you a quick definition. This is called a perfect square trinomial. Perfect square trinomial, and I would give you the definition of that, but I believe it's pretty obvious from the three words that you see. It's a perfect square, because this is a perfect square, but it's a trinomial, so it can be factored into a binomial squared. So now the question remains, what goes in this blank to make this a perfect square trinomial? In other words, what number would go here and here that would multiply to give me that and add together to give me that? And on top of that, what are my signs? Let's go ahead and tackle the signs. We know we multiply two numbers and get a positive, so they must be the same. We've got to get a negative out of this deal, so there's a negative there. That must be a negative also, obviously. So again, what is that? Well, I can't just blurt it out for you. Let's go up here. What's this one? That's 36, because these are 6. How do I know? Well, this better be a perfect square. So we'll only have so many options if we're dealing with integers. So 1, 4, 9, 16, 25, 36. Well, 36, the square root of that is 6, and 6 plus 6 gives me the 12 that I need. So again, this is going to turn into a 6 right here. So let's do one or two more, and then we'll kind of come up with the trick for it, and then we'll get on with the circles. Obviously, this part's not in your notes, so you can just kind of watch. So somebody walks up to you on the street and they hand you this, and it's x squared minus 6x, and they say, hey, that needs to be a perfect square trinomial. What number goes in that blank? And you would respond with, I hope you said 9, and if you didn't say 9, I hope you were at least thinking of 3. Because two numbers multiply together to give me that add to give me 6. So split a 6 in half. Half of 6, of course, is 3, and 3 squared is 9. So here's the trick. To figure out what goes in this blank, you will take half of that and then square it. Half of 6, 3 squared, is 9. X minus 3, x minus 3. Obviously, we can begin to skip this middle step right here because we really know where we're going with this. So let's just cut to the chase. Let's make a really challenging problem, and we'll get on with circles. So x squared plus 5x plus something, and then we're going to have something squared. We know it starts with an x, and we know it's a plus, okay? So now the question is, what goes in this blank? Now, a second ago, I was talking about how they're integers, so it better be a perfect square. Well, it's going to be a perfect square, but it's not an integer in this case, because we are going to look at this and say, well, I need half of 5. Don't say 2.5. Let's not go there. Let's deal with fractions. Come on. We're big boys and girls. We can do this. Half of 5, you take half of that, and then you square it. So when we square 5 halves, well, any fraction that we square, we'd square the top, and we'd square the bottom. We'd square the numerator, and we'd square the denominator. And so therefore, this number is going to be 25 over 4. So now the question is, what goes here? Well, two numbers multiply together to give me 25 fourths. If I add them together, I will get 5. Let's back up for a second. How did we turn a 6 into a 3? We took half of it. So what's half of 5? We've already decided what half of 5 was. We figured that out. a minute ago. There we go, 5/2. And it works too. You could FOIL this. If you were to FOIL this, you'd have x squared, and then going straight to the last one, you'd have 5/2 times 5/2, give you 25/4. And then 5/2 x plus 5/2. 5/2 plus 5/2 is just 5. There we go. So there's the intro to perfect square trinomials. Now, let's mix things up a bit. Let's jump straight into circles. Let me point out something. We're going to be writing the equation of a circle and graphing it in the coordinate plane. And I don't want you to get in your head that this is a function. Okay, real quickly, let me define function and give you a couple examples. A function is just this is a very rough definition, but basically it's something in which you could pass a vertical line through it and it would never touch at more than one point. This is a function. So that green one is a function. Blue one is a function. I dropped my red marker, so let me pick it up. The red one is a function. Okay? Let me show you what's not a function. But I thought we were talking about circles. Right. And circles clearly are not functions. Because if I was going to draw a vertical line through this graph, at any point on this circle other than the two extreme edges where it's a tangent to that, then it's going to touch here and it's going to touch here, which means that I have paired a single x value with more than one y value. I'm just going to make up some numbers here. So for example, this coordinate might be -3, 2, and this coordinate might be -3, 4, and therefore we have paired up -3 with more than one y value. We have one input, x is an input, and we have more than one output, therefore this is not a function. So a circle is not a function, so I don't want you to get in your mind that we're graphing functions like we've been graphing lines or graphing parabolas, because we're not. And therefore the equation is going to look completely different. It's going to look totally different, and it's going to be of this form. And this form is on your paper. X minus h squared plus y minus k squared equals r squared. So let me clarify what a couple of these things are. H, comma, k is the center of the circle, and r is the radius. There we go. Now, keep in mind that in the original form here, r is squared. So if I was to give you an equation and I'm going to say, okay, we're going to have some sort of circle. I'm just going to go ahead and make one up. It's not on your paper. X plus 5 squared plus y minus 2 squared equals 16. And I asked for you to graph it. I asked for you to tell me the center and the radius. Then I think it'd be fairly straightforward and easy to do because you can easily find the center, and the center is at, don't say 5. Don't say 5. No, 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 it's not 5. I want you to look at the original. X minus h. So it's the opposite of what you have here. We've been through this. Anytime there's something inside the parentheses or absolute value bars, or in a lot of situations, if it's inside some sort of grouping symbol, generally you're going to do the opposite when graphing it. So this is not going to be -2. The center is at -5, +2, and the radius is not 16. The radius is the square root of 16, which is 4. We would normally do a plus and minus, but we're dealing with a radius, which is a distance, so it cannot be negative. And if we were to graph it, this should be pretty straightforward. We go 5, back 5, down 2. This is not drawn to scale. And therefore, once we have that center, we can put that dot down. By the very definition of a circle, it is every point on a plane equidistant from a given point. Let me say that again. It's every point on this plane, this flat surface, this equidistant from that point. So it's every single point that is 4 units away from here. So we can go 4 to the right. We can, I haven't marked it, but we could go 4 down, 4 left, 4 up. And we draw a circle, and my circle is probably not going to look too good. That's not too bad. Yeah, it's pretty bad. Anyway, it's every point that is 4 units away. That's 4, and that's 4, and that's 4, and that's 4, and there we go. Okay, I want you to also understand what the domain of this is. Generally, when we talk about domain, we're dealing with functions. And again, this is not a function, but we're going to go there right now because when we deal with composite functions, with things that have been transformed from circles into a function, this is going to become important. Let me just translate what I said. Eventually, we might solve something like this for for y. And when we solve it for y, we're going to get a piece of a function. In the process of solving it, we're going to end up with a semicircle. So if we were to solve this thing for y, we would basically end up with that part in green right there. From here to here. It wouldn't give us the top and the bottom. It would just give us the top. Because again, in the process of doing this, it would give us a square root. And when you have a square root and you're graphing it, you don't do plus and minus. So we have this right here, and we can discuss the domain of that. So real quick, let's do that. So the domain of this, the green part, which would be a function, the domain of this green part is going to go from here to here. It was at -5, and it went 4 this way. So it goes from -9 until we get to -1, and it does include those 2 points. And again, I've thrown that out here because I want you to keep in mind that later on, when we're dealing with things like functions that look like semicircles, or functions that are semicircles, the domain is going to become restricted when we plug it into something else. That should hopefully become more clear later on.